Right, welcome everybody to the June 2026 meeting of the Mornington Peninsula Astronomical Society. And as usual, I'll start off with a couple of things that have happened recently, mentioning there. The big highlight this month is the NASA, the mission to rescue NASA's Swift craft that is plunging back to Earth. This is the one that NASA and the world's astronomers have relied enormously on for detecting sudden outbursts, whether they be gamma ray outbursts and other things. And it's been an incredibly successful mission. Unfortunately, it has no propulsion ability itself in the spacecraft. And with the activity of the sun over the last decade, it's been more active than predicted. And consequently the craft is coming down because Earth's atmosphere has expanded. It was in low Earth orbit about 50% further away than the International Space Station is, but enough to give a bit of friction to bring the craft down. And it's predicted to crash sometime in 2026. So what NASA did with that particular mission is they defied initial attempts by Trump to kill the whole mission and let it just crash back to Earth. Instead they hired a private company to build a spacecraft to go up there and push it into a higher orbit. So this particular spacecraft doesn't have any handles or grappling points on it, or it's never been designed to be manhandled in any way. And yet this craft has to launch up to it, grab hold of it, and push it up. Now in the diagram from the company website there, that's what's being launched up at the moment, the top bit, and this thing here is the actual spacecraft itself, the Swift Observatory. It's been renamed the Niels Gerald Swift Observatory after its principal investigator who passed away. And the launch for that is going to be in a few days' time on June the 27th. Very small launch window available because even when it actually gets up and gets to the same orbit as the Swift craft, this craft here is not filled full of rocket propellant or anything like that. It's xenon ion thrusters, so very, very low force, but over a prolonged period of time. So in other words, it's going to take it months to push this thing from its decaying orbit back up to a higher altitude where they believe it will get another 10 years life before it comes crashing down. Now, it was actually launched in 2024 originally, and it was given a 2-year lifespan. And here it is still working completely perfectly even today. And the fact that it is working so well, and there was so much lobbying from astronomers around the world, because this is one of these patrol telescopes that will pick up something at the earliest possible opportunity. It'll turn itself around and start measuring straight away, but it will also alert all the other instruments to turn around onto a target of opportunity as well. Now, the craft itself isn't going up on a traditional rocket. It's strapped onto a Pegasus rocket, which is on the underbelly of this aircraft. There's only one aircraft in the world that can do this, the Lockheed L1011, and that is the last remaining one of those aircraft in service anywhere around the world. Now the craft is, this service craft here is already inside the Pegasus rocket and mounted underneath it. So in the next few days, if it's not covered in the news at all, you'll at least know it would have happened. So they're taking it out to the Marshall Islands, then they fly up to high altitude, drop the Pegasus rocket, let it fall down a little bit, and then the rocket ignites and takes it up to low Earth orbit. Yeah, so
do they have to move this thing?
Well, at the moment it's getting down to the height of the International Space Station or lower, and it was 600 kilometres up rather than 400 kilometres.
So they need to push it up?
They need to push it up a couple of 100k, yes. Yep. Now this little thing here has 3 arm grabbers on it that sort of come out and try and wrap themselves around the spacecraft. And they've digitised the spacecraft, every aspect of it, because the craft is moving so quickly that it can't actually manoeuvre itself in time if it relies on signals from the ground. So this is very much driven by AI and entirely autonomous navigation. So it will determine whereabouts on the craft it needs to grab. It will move itself around, orient itself around to be the optimum place. Because, as I say, there was never any intention to service this spacecraft. It was just going to burn up after 2 years. And so what they have to do is be careful not to damage the spacecraft in any way by these arms grappling with it and trying to point it in a different direction and upwards. So that's all going to occur very soon. And as I say, it's a private company, and there's only one possibility was this. A launch couldn't be scheduled in time anyway if it was done from like Cape Canaveral. The particular orbit of the Swift Observatory there was also very difficult to get to from traditional launch sites. So that's what you're going to hear a lot of in the next couple of weeks, I would think. Over here, the International Academy of Astronautics, their SETI, Search for Extraterrestrial Intelligence, has reviewed their previous protocols for what to do if you detect ET in signals or via any means. And they've come up and they basically reviewed it. It's been in place for 15 years, but they've now changed things a bit to make it much wider verification before you wave the "we found aliens" flag, right? So lots of different instruments have to confer on it, and different locations as well, before they'll consider it as a positive. And there's no automatic reply to the signal, no sending some signal back to it until the United Nations signs it off and agrees unanimously on behalf of all of mankind that you're going to send a signal back to this alien civilization. So get an out of office reply, yeah. Or Outlook will probably not work or something like that, yeah.
Come to MPAS, no one will be responsible for it.
Yes, yeah, indeed. So they've signed it off, and they've now got to take it to the UN to ratify the protocol themselves.
So I guess the station.
Yeah.
Yes, it's the same thing.
Ah, right. Okay. Yep. NASA announced the Artemis 3 crew. This is the one that was originally going to land on the moon, but it's now going to go into orbit and test some of the procedures, much like happened with the Apollo missions originally. They didn't race off to the moon. They tested the docking and all the procedures to make sure it was okay. So probably wise. This time it's 3 men from NASA and 1 from the European Space Agency. And they didn't pick any women this time, and it was noted online the absence of women this time. And but they did actually have one person of colour, I believe is the term in America, so that they didn't completely whitewash it. About a month ago, the Psyche mission zipped past Mars to use the slingshot effect of Mars's gravity to push it on its way out to the asteroid belt. And Psyche is the mission that's going to go to an iron-rich asteroid there, thought to be a core of a broken up planet. So effectively like a 280 kilometre diameter lump of metal. So pretty valuable if you're a mining company, I would think. So it's now flung its way past Mars. The flyby of Mars boosted its speed by over 1,000 kilometres an hour, so it gave it quite a kick on its way, and now it's off to the asteroid belt. Should get to the asteroid, I think it's 19 Psyche, so it must be a fairly large asteroid to have such a small number. And shouldn't get there until 2029, so it's still a few years away to actually get there. So it's not exactly travelling the fastest possible. The advantage of flying it by Mars as well was that they were able to turn on all the science instruments and point them at Mars to make sure that they were working, and also to help calibrate them as well as they're moving out into darker areas of the solar system. So tonight, welcome everybody, and new members. I don't think we have any new members here, but new members since we last met are Colin Rock, Zhongcheng He, and Ross Stevens. If they see this, feel free to approach the secretary, Nerida, at any time by email, and she'll help make you welcome to the society and point you to some things. As usual, I'll quickly go through the events of the past month and the coming month. It's been a fairly quiet past month, but the coming month is getting a bit busy, especially with Science Week coming up, because all the schools suddenly come out of hibernation and want things done for astronomy, because it's obviously in the curriculum this time of year, and they all sort of come at once. Then I'll throw over to Chris for the Astromofo. Sky for the month is Guido. For those eagle-eyed, you'll notice that Guido's not here. He flew in from overseas last night and will be completely wrecked today, as you could imagine. But we'll put Sky for the month up when it goes up on YouTube, when the meeting goes up on YouTube instead. So he'll be recovered by the weekend, hopefully, for that. Then we'll look at astronomy using a microscope, given by Professor Monica Grady, very well-known astronomer there with one of the missions, the Rosetta mission, and she's the commander of the Order of the British Empire. Then we'll look at what does space smell like by looking at an astrobiologist who happens to also be a professional perfumer, who's put together the smell of various things in space. I tried to actually get samples of it from her, but they have not arrived as yet. But when they do turn up later in the year, as they've probably been sent off via Mars or something to get to Australia, I will then hand it round so people can have a smell of what the various parts of outer space smell like. And that's quite an interesting twist on things. Then to close, we'll look at the highlights of the Swift Observatory over its first 10 years of operation. All right, recent events here. Shown in the background there is the map of the Briars site, the aerial map. This was put together by John Cleverton. And if you look really carefully, so this is, oops, I'll get my pointer there. This is our site here, and you're here at the moment inside the main building. And the new leased area is shown over here. And as you see, it's adding about maybe a third of extra area to this site. So it's a decent additional extra site with the lease. 23rd of May, we had a working bee here in the members' barbecue. Then 27th of May, we had a committee meeting. There was a lot discussed in the committee meeting. There was the fencing, which is the fencing of the new site, and Chris has been talking to the Shire about that. The Society's applied for a quarried grant. Not that we're proposing to dig up the site. It's a way of potentially getting extra gravel and that we can put down on the new site, as well as up here as well, where it.
Can we get concrete?
It might come. It might come in not mixed form, and you have to mix it all up yourself.
If we get the gravel, I can bring some cement and just mix that up.
Oh yeah, that's a good idea.
The remote observatory up northeastern Victoria fell through. It was we were gazumped by a private buyer there who was associated with the company that owned it. We've also have the astrophotography workshop, which is now the preparations of that are now kicked off seriously. So this is the one beginning of October that we hold once a year. The emergency management plan was talked about as well, and that's nearing completion for the Briars. And the cosmology group is going to have an annual cosmology public day on a Saturday afternoon in November, and they've only just picked the date today. I noticed November the 14th, whereby members and the public can come along to that. And it's sort of like an APW, but not quite anywhere the scale. of an APW, at least not yet, but who knows what time will bring if it proves popular. 30th of May we have the next cosmology group here at the Briars on that Saturday. Then the public night, Manfred talked to 71 visitors. He was lucky not to get any cloud on that day. A few days later we had the Jewish Orthodox girls here at the Briars. They were senior students, so year 10 and 12, and Catherine gave that talk, and they were lucky enough to not have any cloud for the time that they were outside under the telescopes. And the public Indigenous night at the Briars, we had about 2/3 of the bookings actually show up. So we only had 27 for that one, but the cloud was pretty ordinary that night. Coming soon, we have rabbit control across the Briars from 6:30 p.m. on those dates, so don't come up here on the 16th, the 21st or the 25th of June, otherwise you might get a surprise. 18th of June, which is tomorrow, we've got the 1st and 2nd Mornington Scouts. 50 of those will be here at 7 p.m. and Catherine and I will give the talk on that one, so we definitely need more help with telescopes on that one. On Friday, there's the Echo House is running their usual winter lantern making. I think they run it inside the geodesic dome next door, and then they come over here for a quick look through the telescopes, and usually Phil gives them that because it's a fairly small number and it's relatively quick. And they have to get out because at 8 p.m. the rabbit shooting begins on that day as well, so they have a natural deadline, so they can't spend all evening looking through telescopes. 20th of June, which is this Saturday, we've got the Working Bee, and I believe the Astrophotography group is going to be at the Briars this Saturday as well. That's after the barbecue, I take it? Yep. 22nd and 23rd of June, so that's 2 nights next week. We have Patterson Lakes Primary School here, 7 o'clock on those 2 nights. And this is like a whole of primary school event from kindergarten to year 6 on those 2, and it's 100 on each of the nights. So as you see, things are sort of warming up a bit now that Science Week is approaching. 24th of June, the next day, we've got the Red Hill Scouts here. About 100 scouts are due to turn up from there. So I don't think it's just Red Hill. I think they've managed to bring in Cubs and all other surrounding areas as well to try and fill the place, because the seats out at the moment will handle 100 without any problems, and at a bit of a pinch we can get it up to about 115. Committee meeting's been deferred a week because of that Scout group meeting, which is the usual committee night, so we've put that off a week. Then 3rd of July we've got the public night here at the Briars. We've currently got 100 books, so it's fully booked, and indeed there's people on the waiting list for that one. And we're hoping Guido's over his jet lag by that stage, and so he's down for that talk. 6th of July we've got Presbyterian Ladies College here for some International Astronomy and Astrophysics Olympiad. So these aren't your usual senior level students. These are the senior level students who are so good that they're competing in an international Olympiad for astronomy and astrophysics, and this is high school level. So the members coming along on that night might get asked some curly questions, so beef up a bit on the telescopes outside and see how much they know. 11th of July, the Cosmology Discovery Group is here on that Saturday as well, and this meeting next month is the annual general meeting where people who wish to nominate for committee may do so soon. Nerida will send out a notification on eScorpius about that probably in the next few days, and the usual monthly meeting as well.
And welcome to AstroMofo number 32. The last challenge was for members to take images of Antares. The first photo that I've got up here is by new member Amy Tang, who imaged Antares, the Antares Nebula and M4, the globular cluster, from here at the Briars on the 10th of June. It was a pretty clear night, so there's actually quite a few of us here that night doing a bit of imaging. There was probably about about a dozen of us, 10 to 12 of us on the scopes with cameras, and yeah, it was a pretty good night. And Amy actually stayed back pretty late to get this one. She got quite a few hours of imaging, and I think she ended up leaving at about 3 p.m. or something. So she was quite eager to get a good shot, and yeah, she managed this one here. So this is with an 85mm refractor with an L-Pro filter. L-Pro is a light pollution filter, and there's about 220 minutes of imaging on that. And in the image, as you can see, we've got Antares, the bright star, on the right, M4 at the top, and Sigma Scopio to the left, which is where we get that red nebula around that as well. So well done, Amy. Just a few quick facts about Antares. So it's also known as Alpha Scorpii, and it's the brightest star in Scorpius. And it's also known as the heart of the scorpion as well, being just in the middle of the scorpion's body there. It's around about 550 light years away. It is a red supergiant with around about 13 to 16 solar masses, and it has a radius of around about 680 solar radii, which puts it out at around about, if it was in the centre of our solar system, it would probably be out to the asteroid belt and definitely swallowing up Earth and Mars as well. And it is expected to go supernova in probably, around 1 to 1.4 million years or so. So nothing that we'll be around for. Now we've got quite a few contributors to this challenge, which is good to see, because I was hoping for a lot of images, and as you saw in the last photo, it's a pretty colourful part of the sky. So Amy Tang, as we saw, myself, I got an image, Chris Kostokanellis, Fred Prater, Greg Walton, Kelly Clitheroe, Mark Stevens, Michael Barrow, Michelle Sykes, Neville Drake, Nick Exaris, and Sylvie Grandit all managed to get images of Antares using different equipment and different focal lengths. And this was one of mine using a 300mm Nikon Nikkor lens with a Antilla tri-band filter, so a 3-colour light pollution filter as well, of Antares and M4. And also the little blue nebula that we see in the bottom there is IC 4605, and it's also known as the little the Blue Angel Nebula. So quite an interesting feature there, which I'd never actually noticed before. Fred managed to get this shot here as well with a 105mm lens. So you're seeing a lot of these photos aren't necessarily through telescopes, because the area is actually quite large and there's quite a lot happening with the nebulas through there. You get really good photos using shorter focal lengths and camera lenses rather than long focal length telescopes. And this one's here with a 105mm lens and a ZWO astronomy camera taken by Fred, who's here this evening as well. So thank you, Fred. I've got a couple of photos by Greg on the 200mm Newtonian. So you obviously clearly see Antares in the middle over here. Hang on, where's my pointer? Clearly see Antares in the middle of this and just to the edge of this one here. Now there is also another little globular cluster in the area there which sometimes gets lost, and that one is NGC 6144, and just to the top here is the outer stars of M4, the larger globular cluster. So the tighter view with the telescope doesn't actually catch the globular cluster as we saw in the other photos. And Greg managed to get these ones here with the wider lens set up on the small astronomy dome in the David Girling dome as well, which has got an EQ5 in there. It's got a plate ready to go, so if anybody wants to put a camera on there, they can actually do it and get some tracked images as well. And this is with a 135mm lens. And what you see in this image here is we've got the Antares Nebula M4, but we've also got the Rho Ophiuchi cloud complex, which is this region over here. And Rho Ophiuchi is actually this star over here. And there's a little bit of reflection nebula or nebulosity around that star. And you get the dark nebulae and reflection nebulas happening in there, which add a lot of character and texture to this part of the sky. And what we have next is an image by Kelly Clitheroe, who sent this one here, which is a much longer exposures and able to get a lot more of the colour. So we're getting the Antares Nebula around here, and that's the star Antares. We've got M4 and that other smaller little globular cluster there. And then we have Rho Ophiuchi over here. And then you've also got the dark nebulas and another reflection nebula over here, and the Blue Angel Nebula that we saw earlier over there. So again, this is with a 135mm lens, so a reasonably wide field of view, captured by Kelly down in Clifton Springs. We've got some C-Star contributions, so thanks to our C-Star operators, and also a Vespera image by Neville. So Mark Stevens is the first one here, and his framed Antares down here on the bottom and M4 in the middle of the image, and you're able to make out the other smaller globular cluster over there as well. Michelle Sykes has got a similar field of view with the NES 50, but she's got it in EQ mode, so she's got a wedge on it, which makes the C-Star work like an equatorial mounted telescope. And Neville's got one with a Vespera too from the Box Hill Spa Observatory. So thanks, Neville, for those. And Neville's actually got the Antares and M4 over here, and he's also managed to capture Rho Ophiuchi up in the corner up there as well. Michael Barrow sent this one through. So a wide field of view of the Scorpion sitting on a rock. The rock in the foreground is actually Uluru. And we've got Scorpius over here just sitting above Uluru through here, and Antares just in the middle there. So you can see from this image why it's the heart of the Scorpion, with the body of the Scorpion here, the middle of it there, its tail swinging around through there, and then the head and the claws of the Scorpion over there. So he got this as a single image that Michael captured, and he did a bit of processing on it to come up with this finished product using Cyril and free software. So that's a pretty good final result from Michael, and you're able to see the dark nebulas through here coming down of the Rho Ophiuchi complex, if that's coming up on the big screen. So well done, Michael. Nick managed to capture quite a few colours as well. So Nick Axaris sent this one through, again with another wide angle lens, 120 to 300mm lens. I'm not sure of the focal length that is used, but I'm guessing it's probably around about 120mm. It looks reasonably wide. And that's why also he's captured, you can see the refraction spikes around Antares. So you've got the little spiky star bits over there, which are characteristic of camera lenses, and that's caused by the iris on the camera. You've got a multi-faceted iris on camera lenses, which shrinks and grows to control the aperture, and that causes those diffraction spikes. Sylvie managed to get a couple of shots as well. Obviously we can see Antares, hang on, no point of pointing it at the laptop, there. So Antares over there, the Antares Nebula, and then the other familiar features that we've seen in the other photos there, and some nice red colours coming out. So well done, Sylvie, with her, that was actually with a Red Cat 51, which is about a 250mm focal length, and a 2600 MC Pro camera, so good stuff. And she's actually labelled it for us here as well, which is a little bit hard to see, but we've got M4 over here, NGC 6144 there, NGC 4605 over here, which was the Blue Angel, and then another reflection nebula here, and the Rho Ophiuchi and the nebulosity around that over there as well. And another image as well from Sylvie. So this is on another night. Was that the same photo, same image? No.
It was
the same night.
Monday night.
Yeah. Yeah, and again, picking up a lot of the nebulosity and the dark nebulas coming through there. So, yeah, well done everyone for capturing those images, and pretty much exactly what I was looking for when I set the challenge, because it's a really colourful part of the sky. Obviously, you're able to image it with a lot of different types of equipment and capture all the different objects that are in there. So well done, everyone. The next one is we're shooting Sagittarius. So Sagittarius next to Scorpius, we've got Antares is there, which we just imaged, and then Sagittarius is coming up a little bit later in the evening, but not far behind. So by about midnight or 10 p.m, it's actually reasonably high and able to image it quite well. But I'm running this next challenge over 2 months because I may not be at the next members meeting. Going on a bit of a holiday, and I may not make it back in time, so we'll We'll have to see, but I will run this over 2 months. Sagittarius has got quite a few different targets to image in there as well. Now Sagittarius is often depicted as a centaur, as we see over there, drawing a bow, but more commonly we know it as a teapot. So that's the teapot structure of it through there. And the spout of the teapot, which is just through here, is pretty much pointing at the center of the galaxy and close to where Sagittarius A star is in the middle of it. And extra credit will go to anybody who can get an image of Sagittarius A star. We've got the Lagoon and the Trifid Nebula in Sagittarius, M8 and M20, which are always good targets. There's plenty of globular clusters, open clusters, planetary nebulas, and all sorts of things to image in there, either if you want to go wide field or with a telescope. So hoping to see some more great images. Any questions?
You mean down in the bottom right there, Antares?
Well, no, that's
just copy.
That's a carryover. That's a copy and paste error. I'll have to sack my editor. Any other questions? Any good questions? All right, thanks everyone.
Hello and welcome to Sky for the Month for the rest of June and the first half of July 2026. So let's start as always with a look at the solar system from above. So this is the view of the 21st of June, so a few days ago. And what we can see here is Earth down here, and we can see Mars up here, and then Mercury and Venus on the other side of the Sun here. So as always, you can see that anything in this direction here is in the evening sky, whereas everything up here is in the morning sky. So let's zoom out a little bit and have a look at the outer planets here. So the outer planets you can see here are Jupiter, almost opposite the Sun now, and then Saturn and Neptune also basically in the morning sky there, and Uranus a little bit closer to the Sun from our point of view. Let's zoom back in and fast forward through the rest of the month. So we can see that we are catching up with Mars, right? Earth is moving a bit faster than Mars. So that means that Mars will rise earlier and earlier. And around this time here, around the 13th of July really, Mercury will pass between us and the Sun. So that's when it's at its inferior conjunction with the Sun and won't be visible. Venus, you can see here, is almost at a 90-degree angle between the Earth and the Sun. So it'll be very high in the evening sky and a very nice opportunity to observe. So let's have a look at the all-sky view for the 1st of July in this case. So on the 1st of July, sunset will be around 5:30. So let's wait a little bit. So actually 5:11. And of course, we've just come out of the solstice, the June solstice on the 21st of June, which was our shortest day and the longest night. So from now on, the days will start getting a bit longer and the nights a little bit shorter. What we can see here, around 6:15 in the evening, we can see Venus as a very bright evening object, and you can see Jupiter and Mercury both very close to the horizon, both heading towards their conjunction with the Sun. In the case of Mercury, it's the inferior conjunction, so where Mercury will pass between us and the Sun on the 13th of July, whereas Jupiter is, of course, an outer planet, so it can never pass between us and the Sun. It will be behind the Sun from our point of view later on in July. So you can see they're very close together, very close to the horizon here, but one is way on the other side of the Sun, whereas the other one, Mercury, is basically between us and the Sun. All right, you can see the moonrise here around 7 p.m. on the 1st of July. We'll have the full moon on the 30th of June, then the new moon on the 14th of July, and another full moon on the 30th of July. So here's the view around 10 p.m. now. And you can see a lot of the bright stars are very close to the horizon. So if we start in the southwest, we have Canopus, then Achernar, Fomalhaut going clockwise, Altair and Vega, all very close to the horizon around 7 p.m. The only kind of really bright stars that are very prominent at the moment are Antares, almost straight overhead, and then Spica and Arcturus in the kind of west and northwest. And of course we have the two pointer stars, Alpha and Beta Centauri, and the stars of the Southern Cross, also pretty high in the sky around 7 p.m. If we have a look at the constellations around this time, the dominant one at the moment in the middle of winter is Scorpius and Centaurus, so both of them kind of in the core of the Milky Way and almost straight above at around 7 p.m. So if we continue through the night, we can see nothing much happens except that the Milky Way is straight above us for almost the entire night. Neptune now rises around midnight, Saturn around 1 a.m. So they rise earlier and earlier now over the next few months. And then in the early morning around 5 a.m. or so, we will have Uranus and Mars also join them in the sky. Sunrise on the 2nd of July will be around 7:36 a.m. A quick look at the apparent sizes of the planets here. So we can see Mercury is almost not illuminated at all because it's so close to the Sun, whereas Venus is a nice crescent shape, so that's exactly at this almost 90-degree angle between us and the Sun. So it's a really nice view through a telescope where you can see the crescent shape there. Mars will be getting bigger and bigger over the next few months as we catch up. While Jupiter looks pretty big here, as I said earlier, it will be on the other side of the Sun and unobservable for a while. We have one interesting conjunction coming up on the 5th of July in the early morning, and that's when Uranus and Mars will be within less than a degree of each other in the sky. So that might be a really nice thing to observe through a telescope, where you can see Uranus as a small bluish disk and then Mars as also pretty small but slightly larger reddish orangish disks as well. So you should be able to get both of them in the same field of view through a nice eyepiece there. And the best time to observe here is just before sunrise, so maybe around 6 a.m. or so. We don't have any comets brighter than magnitude 10 in the skies at the moment. And we have two meteor showers, the Southern Delta Aquarids, starting from around the 12th of July and then peaking on the 30th at the end of the month. The Alpha Capricornids pretty much around the same time also peak around the 30th of July. But both of them will peak around the full moon, so probably not the best ones to observe this year. And that's all for this month. As always, my sources were Stellarium, NASA Eyes on the Solar System, the Astronomy 2026 yearbook, and then a source that I haven't mentioned before, but that's actually really useful. It's Seiichi Yoshida's Comet page that I encourage everyone to have a look at, because the page lists all of the current comets with recent observations and magnitudes and estimated magnitudes over the next months. And there's a special page for Southern Hemisphere observers, so they're always up to date. That's all from me for this month.
Tonight's feature is Astronomy by Microscope. This is Monica Grady there, Professor of Planetary and Space Sciences from the Open University in the UK. She's also Chancellor of Liverpool Hope University and the past President of the Meteoritical Society. She's got an asteroid named after her, so obviously she has a close association with asteroids. And this public lecture was given about 3 years ago at the Royal Society in London. And she was a leading scientist on the European Space Agency's Rosetta spacecraft and its Philae lander. Now, Rosetta you see in the rotating image there. That was the navigation camera of the Rosetta spacecraft as it approached over about a 2-week period, rotating around. And the lander on board was meant to have a nice soft landing, but I don't know if you remember back that far, but when they attempted to land on it, it hit rather hard and bounced off. And the anchors that were meant to fire into the surface and hold it down failed to work, and it bounced out. But with some clever firing of thrusters, they were able to coax it gently back onto the surface. over a period of time, and unfortunately even then it didn't land in a good orientation. It was sort of like pointed off to one side, but they were able to get images from the surface of Rosetta regardless of that, so they got a lot of value out of it, but not as much as if it had been a perfect landing as they would have liked to have planned. So that was on the Comet 67P and Churyumov-Gerasimenko. Oh, that's a mouthful from its discoverers. Now, this talk goes for about 50-55 minutes. If you wish to get up at any stage and have a drink or a natter outside, please do so, and feel free to come back in.
Good evening, everybody, and thank you very much for coming here, and thank you to those who are joining us online. It's a huge honour to be awarded this prize, and I just want to give an aside here of the last time I did anything that was associated with Michael Faraday. And this is again the Royal Institution, and it was the Christmas lectures given in 2016 by Saiful Islam, a chemist. And he was talking about light and electricity, things that Faraday has, well, certainly the electricity Faraday was associated with. And so for Saiful's entertainment and the entertainment of the Christmas lectures audiences, I sat in a Faraday cage. Now, I don't know whether this was Faraday's original cage, but it was really ramshackle, so I think it could have been. So it's a wooden sort of hut thing, and it's covered in chicken wire. And what happens is when you put a great big voltage across it, you don't get an electric shock because the metal of the cage disperses the shock. So they had me sitting in this cage while God knows how many hundreds of thousands of volts was put through it. And if you look at Saiful's lecture, you know, it shows me sort of cowering in this little cage. But I did that for you know, dramatic purposes, because of course I knew that I wouldn't get hurt by the electricity as long as I didn't touch the cage. And of course Faraday cages or Faraday buckets are what we use in a lot of our instruments to collect and count the electrons or the ions that we're looking at for when we do things. So I work with Faraday on a daily basis. But so first of all, my talk, astronomy by microscope. Let's start off with astronomy by telescope, which is the usual thing. That this on the top there, that's the James Webb Space Telescope. It's been sending down some absolutely fantastic images, just really, really wonderful. And this on the right here is an image, you know, as far back in time as we can go. And that image is about 400 billion light years across, or something like that. Oh, it's huge, it's enormous, it's just big. And each of those little bright spots in there is a galaxy with 100,000 million stars in it. And there's just lots and lots of them. This, at the bottom, is also a telescope. This is a lander-based telescope. This is one of our telescopes on the in Tenerife, where we can't take pictures quite as spectacular as this one of all the galaxies, but we can take amazing pictures of solar system objects, and it's part of our teaching things that we do. So, you know, astronomy then by microscope. These are the sort of things that I use instead of telescopes. And whereas before something was several hundreds of billions of light years across, this is now, well, it's about 2 millimeters across there, all right? So we're looking at something at a rather different scale. This is a microscope. This is an optical microscope, and it produces images like this. These are two images, one in what we call plane polarized light. So that's just light going into the microscope. And this is what happens if you put a pair of sunglasses on it. So the light is polarized, and you get those amazing colours there. So that's this. This is a scanning electron microscope. So this is using light, okay? This is using electrons, and we get pictures like this, which tells us the shape, the topography, the bumps in the sample. And this is a map of aluminium, calcium, and iron, and it shows that we've got different additions. If you add magnesium, iron, and calcium in, and you've got more magnesium, you get this. If you've got more calcium, you get this. And this tells us about mineral compositions. And then this thing, and I use both of these, all right? I'm allowed, I'm qualified to use these. This thing here is called the nanosims, all right? And instead of using a beam of light, photons, or a beam of electrons, it uses heavy ions, right? It uses cesium usually, so that's a very heavy thing, and it bombards the sample, and instead of, just bouncing back nicely, what it does is it drills holes in the sample. And although I beg my colleague, Ian Frankie, to let me use this, he says, no, Monica, no, it's beyond you. Your students can use it, but you can't. All right, and what it does is it produces some maps like this, but it produces data, all right, on isotopes, and we'll come back to what isotopes are. So there are three different types of microscope. And this is what I want to try and convince you this evening. And there's a phrase here which I really don't like, and that's ground truth. Data from meteorites provide ground truth for astronomical observations and astrophysical models. And what that means is, if you're an astronomer and you've taken a lovely picture of a galaxy or something, you can think, oh, well, it's this colour, it's this size, it's this age, it's probably doing this. And then we can actually trace some of the things that have come from those processes, what's going on in the galaxies, and we can measure them. We can hold them in our hands. They're real, they're there. They're even more real and there than an astrophysicist's model. Modelers, they can model anything. They can do whatever they want. They can say, well, given these parameters, and it's like, yeah, well, where did those parameters come from? We put those parameters in there. We say, well, you've got to start with this, because we have measured it. It's there. So that's what I mean by ground truth. And we use these techniques. I've shown you the pictures of the optical and the electron microscopes. We also use microscopes that use X-rays, and you get the structure, just like when you X-ray your hand. You can X-ray a rock, and you can see the structure of the rock. And we use spectroscopy. So, a rainbow is where the light, white light, has been broken down into different colours based on their wavelength. Well, we can use all sorts of wavelengths, much wider, much broader than just the visible wavelengths. And we can also divide samples in terms of what their mass is. So if you've got a whole chunk of sort of organic stuff, and you can put it into a mass spectrometer through a column, which teases out things depending on how fast the molecules can move along that column. And the little ones move ever so fast, and the big ones are really much slower. So you can tease them out like that. And then this here is what our nanosims would come under. So we can analyse all sorts of the astrophysically significant materials, which is what I'll come to and talk about those. And then you've probably all read this already. Astronomers often have to go out to telescopes where it's cold. And sometimes if it's cloudy, if they're looking for visible light or infrared or something, it's cloudy and they can't see anything, it's tough. In a lab, it's never cloudy. We're not allowed coffee in the labs anymore, which is the drawback, but there you go. Don't have to worry about clouds. So this is the cycle, all right, the star formation cycle. And yes, I'm still talking about images that we've had from telescopes here. And where should we start? I mean, this is the problem, because it's a cycle. And we're not exactly sure where we start. Do we start with stellar evolution? So we've got a star, like the sun, It goes through its life cycle. It's going to become a red giant, and then it's going to become a white dwarf. Some different types of stars explode to become a supernova. And when the star explodes as a supernova, all the material, all the matter that made up that star gets thrown back out again. It gets thrown back out again into the interstellar medium, which isn't just the space between the stars, but that's the easiest way of thinking about it. Now, the interstellar medium, space between the stars, the space between the galaxies, and so on and so forth. There are parts of our galaxy which have got concentrations of gas and dust. The gas is mainly hydrogen. There's silicate dust there. Dark clouds. If a dark cloud collapses, and it might be triggered to collapse by the explosion of a supernova, as it collapses, star formation happens. So you get stars. The stars might form a disk round from the dust around the star, and then the star evolves and eventually might explode as a supernova. And at each one of these stages, material is coming and going through the interstellar medium. And so what we can do with meteorites is we can say, stop. We're going to look at some of these processes that have been going on and find out the information about them. Now, is this going to work? Do I have to do it again? Maybe I do it again. Yeah. So this is a simulation of planetary formation, all right? And it's terribly slow. So we'll probably only watch a little bit of it. But what you can see here is a cloud of gas and dust, and it's turbulent, it's rotating, and gradually the central mass gets bigger and bigger and bigger. And it gets big enough eventually so the mass causes it to switch on. It's a star, it's undergoing nuclear fusion, it's burning hydrogen, and then it can attract dust to it, which can spin round and be clumped together as planets. And I'm sorry, you know, we're still doing astronomy by telescope here. I just get so moved and excited by some of the pictures that you can see. And this, for me, is one of the most exciting pictures I have ever seen. You might say, get a life, get out a bit more, but just, it's amazing. It was taken by the ALMA telescope. Now, the ALMA is the Atacama Large Millimeter Array. I have no idea what a large millimeter is. I thought they were all the same size, but I think it's a large array of telescopes which measure things at millimeter wavelengths. All right, so, and it took this picture of this star in the center and the protoplanetary disk forming. It's a real picture. It's not a simulation. It's a real picture. And for us to get things like this, just so wonderful. Here's another one, right? Again, in the center there, what you've got is you've got a protoplanetary disk. It's a real picture. I just get so excited by them, but you know, I get excited by chocolate as well, but there you go. So what's happened then is once you've had your protoplanetary disk and it started to collapse and it clumps into different things at different places. So we've got our sun, we've got the inner planets, we've got the outer planets, and then we've got something called the asteroid belt, which is a mixture of small bodies, the biggest of which is about 1,000 kilometers across, which are mainly rocky, or stony, and some metallic ones. We've got another belt out here called the Kuiper belt. The objects there are much darker. We know a lot less about them than we do about the asteroids, but they're mainly rock and ice. And this could be where a lot of our comets actually come from, our short-lived comets. Pluto has been promoted. It's no longer a planet. It's no longer the smallest planet in the solar system. It's now one of the biggest Kuiper belt objects. So it's gone through, you know, it's been upgraded. So anybody who says to you, I think Pluto should be a planet, say, no, it's been promoted. It's no longer the smallest, most distant, most not interesting planet in the solar system. It's a really, really, really interesting Kuiper Belt object. So most of the stuff that I study comes from the asteroid belt. And here's 2 asteroids. These were the focus of NASA's Dawn mission a few years ago. This is Vesta, which is I think it's about 500 kilometres across, and this is Ceres, which is about 1,000 kilometres across. Ceres is big enough, actually, to be known as now a minor planet, because it's pulled itself into this spherical shape. Vesta is, it's the classic potato-shaped asteroid, potato or peanut. Depends which side of the Atlantic you are on, whether you classify asteroids as potatoes or peanuts. Anyway, this is potato-shaped. But you can see they've both got lots and lots and lots of craters on them, which shows they've been bombarded throughout the whole of their history. So things have come and hit them. And when things hit something else, bits shatter off. Most of the bits will fall back down, but some of them, go off, wander off, and some of them eventually fall to the Earth as meteorites. Now, these are made of they're very different types. They're both made of stone. But you can see this one, so the craters are quite sharp. This one, they're more blurred. And it's because this is actually more like a ball of mud, frozen mud. It's got quite a lot of water in it, and in fact, these very bright spots here are thought to be evaporites, like we get maybe in a rock pool at the seaside. And so although there's no water on the surface, the minerals it's made of have got a lot of water in, and it's like a sort of clod of mud rather than a rock, whereas this one is a good solid rock. Right, and they tell us about different things. So now I'm going to teach you all how to classify meteorites, okay? The traditional classification is we've got iron ones, which are made of iron, stony ones made of stone, and stony irons, which are a mixture of stone and iron. All right, have you got it? Stones, irons, and stony irons. Can't go wrong. However, a more modern classification, the way we do it these days, which is much more interesting and tells us a lot more about the meteorites, is we think of them as being primitive or processed. Primitive here means they're undifferentiated. That means they've never been hot enough to melt so that they can separate out inside themselves, okay? So these primitive ones have been very, very little changed. They might have been altered a little bit by water. There might have been a little bit of thermal metamorphism, but they've never got hot enough to totally melt. And we call these ones chondrites. And I'll come back to what this odd word is in a minute. And then the other type are the processed ones. These are ones that we call achondrites, because they haven't got any of the classic things that chondrites have. And these have been heated, they've been melted. Some of them have been melted completely, and so that the metal has separated from the rock, just like on the Earth, because we've got a core, our Earth is differentiated. And we can learn different things that have been going on in the solar system from these different objects. Now, this is a classification of all the meteorites. Would you like me to go through it box by box? We'll start off with the sea eyes over at this end and work our way gradually across to these. It'll only take, about 5 or 6 hours, but, maybe we'll skate through that. And we'll just stick with some of the primitive ones, okay? So this is a hand specimen. It's a chunk about the size of my fist, and it's of from an asteroid which has got some carbon in it, and not a huge amount. It's a meteorite which is called Allende. Now, what we do with meteorites when we want to look at them with a microscope is the first thing we do is we saw a bit off them, all right? Now, a geologist, right, which at heart is what I am. A geologist, they look at a rock, the first thing they do is whack it with a hammer, and then the next thing they do is they spit on it, All right. Now, a meteoriticist, we are not encouraged to do that. All right. It's not done. And I'm sure I've never done it, ever. So what we do here is that we would take a section and we would saw it, polish it till it was very thin, until it was so thin that you could actually shine light through it, and that's about 30 microns. Or we might embed it in a chunk of resin and just polish the top. And when we do that, you can look in greater detail at the objects that are in these meteorites, and these round things are what we call chondrules. And that's from a Greek word, chondros, which means droplet or little seed. And that's what the first person to identify them or to see them through a microscope, he looked at them and he thought that they were like droplets of a fiery rain. And that's a really, really great description because, well, we still don't entirely know how these formed, but they must involve melting in some way. Now, what you can see on this one here, the hand specimen, you can see all these very irregular features, including this bit on top, which is not a bird dropping. It's a very irregular feature. And these things are called CAIs. CAI for calcium and aluminium-rich inclusions. And guess what elements these inclusions are rich in? Yes, they've got lots of calcium and aluminium in them. And if you think minerals which have got the calcium and the aluminium in them, they are really, really refractory. You can heat them to really high temperatures. So the lining of an oven, for instance, will be made of ceramics, these things which are what these mineral grains are. So what you've got here is something that's fluffy, it's not a regular shape, and it's made of calcium and aluminium-rich inclusions. These formed at a very high temperature, some of the highest temperatures as the gas and dust of the protoplanetary disk was cooling and minerals were forming. These probably, there's several different minerals in there, but these were probably the first formed things that go into meteorites. The second lot are these things called chondrules. You've got the same picture, you can see the rounded shape. And here's a closer view of one. These are not made of calcium and aluminium. These are made of iron and magnesium and silicon, and you can see they're very rounded. So they've got a different shape, a different texture, different composition, but formed from the same cloud of gas and dust that has formed the whole of the solar system. So what is the process that has caused these two things, the CAIs and the chondrules, to be formed differently? Well, what's happening is you're getting this protoplanetary disk, the pre-solar nebula, is cooling, and you're getting changes in turbulence, in the dust-to-gas ratio, in the amount of oxygen that may or may not be there. And you can see this. There are at least 8, or there were 9, processes that have been thought to produce chondrules. And my favourite quotation is from a very old colleague who is actually in the audience at the moment, so I better say a dear and esteemed colleague rather than an old colleague. When she said, chondrules are formed by the chondrule formation process, whatever that might be. All right, so it's like, and she is an international expert on chondrules and chondrule formation. And that's about as good as we can get. The chondrule formation process, whatever that might be. All right, so it could be that bolts of lightning went through the dust and fused some of the dust grains together. It could be the shock wave from a supernova or the shock wave from something else, or as our protoplanetary disk was traveling through the nebula and it was scooping up stuff. There's all sorts of different ways. Now, when we look at this grain, though, you can see it's got an extra bit on the side. So it must have been tumbling and it's accumulated other bits towards it. So it's helping to actually look at what has been going, the processes that have been going on as the sun was forming. Right, now this is very technical, but don't worry too much. I'm not going to go through all the radioactive decay equations, stage by stage, promise. All I'm going to say is that there are some isotopes that are radioactive and they decay. Uranium decays to lead. I think, we're sort of quite familiar with that. But there are lots and lots and lots of decay systems, lots and lots of different isotopes which decay. So we've got ones that decay over periods of billions of years, or ones which decay over thousands or a million years. And depending on the decay system you choose, you can learn different things. So what actually happens is you have a parent which decays to a daughter. Now, if you've got uranium and it's decaying to lead, what actually happens is, sometimes, the remaining uranium stays in one bit, and the daughter isotope, the lead, likes to go into another bit, all right? Or aluminium decaying to magnesium. You've got one bit going into another bit. So you can actually start looking at the ages of formation things, right? So this is where we go back to the chondrules and the CAIs. We're using a very short-lived system, all right? We don't need to know that too much. So if you've got something and you've got aluminium, which decays to magnesium, and if you've got something and you can find the particular type of magnesium in that mineral that has come from, that magnesium's come from the decay of the aluminium, you can say that that mineral must have been around, it must have been forming when the aluminium was still present to be decaying to magnesium. But because the aluminium has such a short half-life, it's gone after a few tens of short lives, hundreds of half-lives. So you can say, oh, right, actually, this particular mineral has got that brand of magnesium in, so it must have been formed very early on. This mineral hasn't got that brand of magnesium in. Oh, it can't have been formed until after all the aluminium has gone, all right? So this is what we're doing here. We're looking, and we can say, right, actually, and this is a very simplistic picture. It's more complicated, but, simplistically, these that have got the aluminium in, they also have some minerals they've got these minerals with aluminium in, and so you can look for those aluminium-rich minerals and look to see if they've got any magnesium in. And if they've got the magnesium in, then yes, they were formed really, really early on. Now, another aside, I take every opportunity to get at astronomers, because it's fun. If you ask an astronomer, how old is the solar system? They might say, 5 billion years? 4.5? Something like that. We can say that the solar system is 4.5672 plus or minus 6 million years old, all right? That is very precise. 4,567.2 plus or minus 0.6 million years. That is precise and accurate, as we all know the difference. All right, and the age of chondrules is this, 4564.7. All right, so the difference between these two phases that you find in intimate contact within a meteorite, their age differs by 2.5 million years. What's 2.5 million years between planetary scientists, you might say? Well, it's actually quite a lot to keep things separated in a very active and turbulent solar nebula. And so that's why we're still trying to explore this and find out how this has actually happened. But this is something that's very important to understand for nebular evolution. Okay, so I skated over uranium, lead, and radioactive dating. Now let's delve much more deeply into nucleosynthetic processes. That's a good one, isn't it? So, nucleosynthesis. what's nucleosynthesis? Well, it's when things happen with elements. When you've got neutrons around. Some elements can absorb a neutron slowly. And this happens when you've not got very many of them, all right? And what happens is an isotope captures a neutron, and it sits there. It says, I'm waiting for another one. Oh, but there aren't much. I'm going to decay, all right? And so that's what happens. It decays before it can capture a second neutron. Where you've got a lot of neutrons, all right, you've got this. That's S for slow, R for rapid. We do like to keep things simple. So here you've got a lot of neutrons. So you've got a nucleus, an atom. It captures a neutron, and then before anything else can happen to it, it captures another one, and maybe another one. All right, so you've got different types of nucleosynthesis processes going on, and they leave their signature in the elements. And they leave them very particularly in pre-solar grains. So when we look at stars, a star isn't, a thing that's there and it doesn't change. A star evolves in the same way as we evolve, all right? And so this diagram here is a complicated picture of what happens to a star, all right? It can start off big, burn fast, die, or it can become we're somewhere along here, all right? We've got a lifetime of about 10 billion years, and we're about halfway through it. And this is us, and what's going to happen to us is we're burning hydrogen, well, the sun's burning hydrogen into helium, then it'll burn helium, and then it'll puff up enormously into a red giant, and then it'll burn all its fuel, and it'll shrivel down into a white dwarf, and it'll die. It's not big enough to do something dramatic like exploding as a supernova. So what we can do is we find products of these processes that have gone on in other stars. We find them in meteorites. And, sorry, this is a very busy slide, but I tried to get, I tried to reduce the number of slides I've got by putting more on each slide, which is very bad, all right? So, pre-solar grains, they're a minor constituent of chondrites, up to 2% max. They were recognized on the basis of their unusual noble gas isotopic compositions. Xenon has got, 9 stable isotopes? It's got a ridiculous number of isotopes. And sometimes one particular isotope is enhanced over another particular isotope. And so in this one here, the signature, if you've got some gas, some xenon, and you look at it and you say, oh, it's got a lot of xenon-128 and a lot of xenon-132 relative to xenon-130, but hardly any 129 or 131. That is caused by S-process xenon. And S-process xenon is produced in stars which are going through helium burning and various other processes. And they also have very unusual carbon and nitrogen in them. All right, so this is a picture of carbon and nitrogen. And this, at last, some of my data. This is what I do for a hobby. I burn rocks, and when I burn the rocks, the meteorites, I look at the carbon dioxide that comes off, and I can say, oh, if carbon dioxide has come off at about 1,000 degrees C, so I've heated my sample up to 1,000, and it's got carbon, which has got a very low, it's got a high delta 13, so you don't need to worry about that, but it would be plotting down here. So it's something which has probably come from an AGB star, an asymptotic giant branch star, a big star, all right? It's not come from the sun. And these are examples of these types of materials: silicon carbide, graphite, aluminium oxide. I've put for, dramatic purposes, diamonds, emeralds, and rubies, but emeralds and rubies are just aluminium oxide, by any other name. So the other type of material that we've got are these nanodiamonds. They're only 3 nanometers in size. And they've got xenon associated them, which is got a lot of the light isotopes down here and a lot of the heavy isotopes. There is no known astrophysical process which can produce a pattern like this, all right? Now, astronomers, when they can't explain an astrophysical process, They either say it's a black hole or it's a supernova, all right? One or the other, black hole or supernova. Here, we've gone for supernova, all right? So we've produced a huge number of neutrons in the explosion of the supernova, and they've produced little diamonds. Now, again, it's not terribly certain that this is the right answer for the diamonds, and there's some thought that they might be produced somewhere else, but we don't really know. Now then, I'm going to have to move quickly. Where are we? Organic interstellar material, right. So I've talked about the non-organic stuff, the silicon carbide and things like that. But we've got in some meteorites, and this is a picture of a meteorite called Murchison, which is very rich in carbon. It's got about 2.8% carbon in, which is buckets for a meteorite. And most of that carbon is a sort of entangled mass of sort of gunge, really. It's a mixture of all sorts of different carbonaceous components, some of which have got a lot of some of which have got a lot of deuterium in them, and again, these heavier isotopes of carbon and nitrogen. And what's thought is happening is in the interstellar medium, things like the dark molecular cloud, where you've got grains of silicate and they're coated with ice. And what's happening is they're being bombarded by radiation. It might be UV radiation, but might not necessarily get into the molecular clouds, or cosmic rays. And what's actually happening is you get a whole suite of reactions called iron molecule reactions, which leave the solid stuff behind to be enriched in these isotopes. So what we can actually do is we can use this as a tracer for astrochemistry and look at the evolution of molecular clouds when we look in meteorites for these things, which is quite interesting. Now, origin of life, all right? Some asteroids are rich in water and organic molecules. This is asteroid Ryugu, which was the target of Hayabusa 2. And this is Bennu, which is the target of OSIRIS-REx. And this is Comet 67P Churyumov-Gerasimenko, which was the target of the Rosetta mission. Now, this has brought some material back. And it seems to be sort of, we've analysed, one of my colleagues, Dr. Verkovsky, has analysed some of the grains from Ryugu, and he has found that they're medium enriched in hydrogen, in carbon, but they seem to have quite a lot of water in them. This is my bit, can you see? 6 or 7 little black specks there? Yep, they're mine. Which I've been looking at the reflectance spectrum from, and then I'll burn them. Right, okay, so they're sitting there. And so we've had these from this particular asteroid. We'll be getting some back from Bennu in September. They arrived back in September. The Open University is one of 3 laboratories outside the NASA system which are getting these materials. We're one, the Natural History Museum's one, and I think there's one in Switzerland, right? So I think we're the 3 European partners which are going to get some of the material from Bennu. Now, it's possible, these are both look as if they're like the types of asteroid that Murchison came from. We've got a handful, about 5 meteorites, that aren't like Murchison, that aren't like anything else, and possibly come from a comet. Now, the Rosetta mission produced, there was an instrument called Ptolemy, which was built at the Open University, and it produced a spectrum. You can see here, this is the molecular mass of some of the samples that came from, some of the data that came from the mass spectrometer on board Ptolemy, on the Philae lander. And some of these are the signals of alkanes, alcohols, things like that, the types of material, the types of molecules which make up the building blocks of life. So it could be that when the Earth first formed, it was bombarded by this sort of material, and so the water came from or a portion of it came from extraterrestrial samples. Right, I'm going to have to go really fast now, sorry. Processed meteorites, these are the opposite of the primitive ones. Some of them, like the ones that come from Vesta, which is like this, they're the solidified remnants of the solar system's earliest magmatic activity. So we've got really, old volcanoes on some of these asteroids. Iron meteorites, these are the ones that have actually completely separated out. So if you think about how stainless steel's made or how steel's made, you take the iron ore, you heat it up with a catalyst, and what happens is all the iron goes to the bottom of the furnace and you get a scummy bit on top, the slag, all right? Now, the iron in the core of the Earth and the Earth, that's been through the same sort of process. So the core of the Earth is the pure iron with some nickel and other bits and pieces in it. And the bits that we're standing on, we're the slag, all right? So we're the slag on the crust of the Earth. I won't go into the Wittgenstein pattern, but this tells us, this is the closest we can get to the core of the Earth, because of course we can't dig down that far. So going back to our radiogenic nuclides, using different half-lives, we can look and see when an asteroid has differentiated, when the core, the metal core is produced. We've got the mantle, which is rich in a mineral called olivine, and you've got the crust, which is rich in a mineral called plagioclase. And you can look at the time scales of when that happened and when that happened by looking at these different systems. And we can bring up this diagram again. We've got the CAIs here, the chondrules. We've got the chondrite formation, when they all came together to make the solid bodies. We've got the Earth forming here, and then differentiating, and the Moon forming. And it all happened, in a very, very short period of time, really rapidly. We've got meteorites from the Moon. All right, I'm going to try and finish by 7:45, right? So we've got some meteorites from the Moon. We know they're from the Moon because we can compare them with the Apollo samples. We've got meteorites from Mars. How do we know they're from Mars? We haven't got any samples that have been brought directly back from Mars. However, this is a meteorite which was collected in Antarctica in 1979, and it's got these pockets of glass in. And when you dig out a pocket of that glass and melt it, gas comes out. And the composition of that gas is identical to the composition of Mars's atmosphere. Now, this was taking place in 1984, when people were just recognizing that we got meteorites from Mars. That's mine. That's my data point. All right, so we analysed this. This is when we were still over in Cambridge, actually, before we came to the Open University. But that showed you've got the identical composition, and the only way that you could get that gas in those glass clasts is those clasts had to be molten. So it's probably when something hit the surface of Mars, blasted material off, and in that instant, some of the atmosphere was trapped. Now, knowing that we've got meteorites from Mars, we can then go on and say, let's look at them and see what we can learn about Mars from these meteorites. And I hope my good friend Everett is listening online. He said he was going to be. Here you are, Ev. This is our meteorite. This is Allen Hills 84001. And Everett Gibson and his colleagues produced an image in 1996 where they showed this, which is a couple of hundred nanometers, micrometers long. And what they said was that it's possible that this is actually a fossilized bacterium. And the substrate is these, which are rosettes of carbonates, which are produced in warmish, sparkling water, okay? So they had it was a long detective story, a long chain of evidence. And not everybody believes that this is actually a fossilized bacterium, but what it did was it really, literally and figuratively put a rocket up the Mars program. And now, we're exploring Mars like there's no tomorrow. And so at the moment, Perseverance is at Jezero Crater, And sorry, I've got some more telescope images, or at least from camera images. Just look at that. That puts me in mind of Brimham Rocks in Yorkshire. Just look at that. Look at the way it's balanced. Isn't that amazing? It's just like amazing. I can't get over these pictures. Just like, they're so gorgeous. You know, it's just like, wow, they could be seals basking, but they're not. Anyway, so there's a Mars sample return mission coming back in about 2033, when I'll be 75, if, you know, God willing, if I'm still here. I'll be in the lab, pestering the head of school. This here is about 20 centimetres long. This is one of the samples. They've produced a depot, is what they're calling it, a depot of 10 samples. Now, to me, a depot is you've got 10 samples all gathered together. Now, these are about sort of between 5 and 15 metres apart so that they can be readily collected. I don't call that a depot, I call that a string. Anyway, so these are the things, these are cores, which another mission will go to collect. Right, where do they come from? Where do we get them? We get them from deserts. Look, Antarctica, desert. Ice, meteorite, dead easy. Sometimes, though, they come without us knowing about it. And this is a fireball from the Winchcombe meteorite, which fell a couple of years ago now, which is beautiful. This is another beautiful thing. Isn't that beautiful? Isn't that beautiful? To you, it might look like a barbecue briquette, but to me, it's got the secrets of the solar system locked up in it. Mr. and Mrs. Wilcock and their daughter woke up on the morning of the 29th and found that somebody had been throwing things at their drive. And if you look online, you can see through the Natural History Museum, some people went and they've dug up the drive and they've taken all this away, and it's now going to be on display in the Natural History Museum. And my colleague, the one who doesn't know how chondrules are formed, she went with a toothbrush on her knees to get all the bits from that drive. Isn't that dedication? Or stupidity, who knows? Anyway, right, where are we? So, this is my almost last slide. What can you learn from meteorites? Well, the different populations and ages, I didn't go into the age of the pre-solar grains, but some of them are maybe 2 billion years older than actually our solar system. We can learn about molecular cloud evolution. I've talked about that with the organic molecules. We can learn about stellar evolution, the pre-solar grains, the hydrogen burning, or the helium burning, or the supernova. The CAIs and the chondrules tell us how our protoplanetary disk has evolved, which is not just the origin and evolution of the solar system, but the origin and evolution of planetary systems and exoplanets, which is fantastic. We've also got the planetary melting from the achondrites, the core formation from the iron meteorites. We've got the formation and evolution of the moon, the formation and evolution of Mars, and the history and fate of water and possibly life on Mars. We've got the origin of life itself, all from those little poxy rocks. I hope I've persuaded you that we can do astronomy by microscope. And I've just got 2 final slides. I want to thank my friends and colleagues, especially my family, especially my husband Ian. Caroline, this is for you. We went to Houston as colleagues and came back as lovers. Caroline really hates that. No. All right, okay, and so that's my family. And I would also like to thank the institutions that have sheltered me, encouraged me, helped me, especially the ones that gave me money. That's these here. And also these missions. OSIRIS-REx is going to be fantastic when the stuff comes back in September. This, when it comes back next century. And I owe such a lot to the Royal Society for allowing me to give this lecture, but I owe so much to the Open University. The Open University is just an amazing place to work because of its mission to be open to people's, places, methods and ideas, which is just a dream that we can help to educate people who haven't had the opportunity And I love being part of that. And it's really, really important for me to say that to you. Thank you very much indeed.
Well, thank you very much, Monica. Unfortunately, my notes on what I'm supposed to do next have been scribbled all over with comments from your talk.
Oh, sorry.
I know that people out there, if you've got questions, you want to send them by slido.com and enter, it doesn't say up there, enter the code #F6323, or questions in the hall here. There is a microphone that will roll around. We've probably got about 5 minutes max. So a question from outside. Do you have a favourite meteorite and why?
Oh, gosh. Well, it depends what I'm working on. Sometimes my favourite meteorite is Allen Hills 84001, the one from Mars with the clusters of carbonates in. Sometimes it's Winchcombe, the one that fell recently. So I'm really sorry. No, I haven't got a favourite meteorite. I love them all.
And here's a great question. How would you convince an 8-year-old to follow a career in planetary science? Which are the exciting and rewarding bits, and what are the challenges?
Cool. Right, well, hold on a bit, because my grandson's 8 in a few weeks' time, and, you know, I'll ask him. But I think, really, for more and more people to go out and go talk to schools, go and talk to you know, scouts, and really go out, because if the younger children can get the interest and carry it on through those difficult teenage years and then get on to university and carry on, I think, you know, people like Brian Cox have done a fantastic job, you know, of enthusing people and try and make complex ideas understandable and give people an idea of the excitement of things to come.
Question in the second row.
Thank you very much for those interesting insights. Would you compare what it's like for you waiting until the stuff arrives and for some of our colleagues who go out to fetch it?
Oh, interesting, because I've also been out to fetch it, and that's great. You go out in the field, you go to Antarctica, and you see some of the rocks. And I remember when I was there, the guy who was leading the expeditions, Professor Cassidy, he just looked at us. There were 4 newbies who'd never been before. And he just said, "You're like fish in a feeding frenzy." We were zapping backwards and forwards trying to pick up all these meteorites. It was amazing. But you then have to let them go. They go to a curation facility and they're not your meteorites. It's not easy to compare what it's like waiting for a sample to come back, because things happen all the time. I mean, like, we're waiting for the samples to come back from Ryugu and from OSIRIS-REx, and Winchcombe falls, you know, and it's just, and right in the middle of lockdown. Oh, I know, let's all go over to Cheltenham. Oh, it's lockdown. Yes, health and safety forms in the universities. But yeah, I don't know, I can't answer that question really, sorry.
We can probably squeeze in one more in the second row.
Thanks. Monica, you explained about how we could tell those meteorites were from Mars because of the glass and the composition of different elements that came out of the gas that was in the glass. But how do we know what Mars's atmosphere is made from?
Oh, because this was going on in 1983, 1984, the acceptance that these came from Mars. There was the Viking orbiters and landers in 1977, which measured the composition of Mars, and they found out, and Mariner 9 had also found that the atmosphere was mainly carbon dioxide, and it had a very, very particular carbon 12 to 13C ratio, and that was mimicked. The relative abundances of the different molecules and their isotopic composition.
Any last comments, questions? Otherwise, I slide across here, because the real thing of the evening, apart from thanking Monica for an astonishing presentation that's taken us back 4, 5, 6, 7 point something years. I love that. But really, It's a great honour on behalf of the Royal Society to present Professor Monica Grady with the 2022 Michael Faraday Prize for her expertise in communicating science, and I think we saw that tonight. Congratulations. Fortunately, I did not scribble across the thing that says, and remember to present Monica with the scroll and the medal. Congratulations,
Thank you very
Monica.
much indeed. Thank you.
Now we'll look at what does space smell like, and before we look at that, that goes for about 9 minutes or so. I have an interesting contraption here from John Goodall, who's brought it along, that if anyone wants to make a blink microscope or a blink comparator for photographs, if those of you that remember how Pluto was discovered, you would use something like this. So if you're interested in it, come forward afterwards, and John's sitting at the front there. Feel free to come and have a look at it as well, even if you don't wish to build one yourself. Okay, now this is by Marina Barcinella, who's a astrobiologist and a perfumer.
My next guest will be taking us into outer space, but not quite in the way that you might expect. For the majority of us who are unlikely to visit space, Marina has invented a surprising way for us to experience it. And that is Arum Atom. Marina, welcome to Summer Science Live, and thanks for joining me. Now tell me about what this surprising way is. How can I experience space in the Royal Society today?
Okay, so my special way to help you experience space is through your nose.
Okay.
So I'm very keen on making sure that people use all their senses when it comes to learning. And when it comes to something like space, it's so far away, so distant. And as you said, most of us are never going to go there. So the only way we can experience it is through your senses here on Earth. And there's loads of images, there's even sounds from space, but smell is something that if you go out to space, you're not going to be able to smell, because obviously you need to have a helmet on to be able to breathe. But the chemistry of space is out there. So what I have done is try to bring the chemistry of space to Earth so that we can smell it here and experience that dimension of space, that it's almost beyond anybody's ability, really.
That sounds so fascinating. So what have we got here in front of us now?
Okay, so what we've got here are 3 smells that I've chosen for you. So let me just get them here. I think that is Mars. We're going to go to the first one, which is the closest one to us. So this is something that mimics what we think the smooth, sorry, my Spanish is coming through, what the moon might smell like. Now, we have accounts from the Apollo astronauts telling us the smells that they experienced after they went out on their moonwalks, came back into the spacecraft.
Okay, don't tell me what they said. I'm going to have a go, and you can tell me after I have a sniff.
I won't tell you, but so they've said things, and that's what I have tried to create in here. So before I tell you any more, I'm just going to let you smell it and see what you think.
I feel like it smells a little bit like peppery.
Okay.
Maybe a bit, I don't know, like after something's burnt in a room or something, maybe? What was the astronaut's take on?
Okay, so what you're smelling is something that sort of tickles your nose, and there's a smokiness to it as well. And there's a reason for that. So the first one is the accounts of astronauts tell us that the majority of them agree that it smells something like spent gunpowder. So I've never smelled gunpowder, but if you imagine the smell of fireworks after a big firework display, I was trying to capture something like that. However, when you look at the mineralogy of the moon, it wouldn't smell like that. The minerals that we find on the moon would be pretty much odorless. So the most you would get is maybe some form of mineral kind of note, like earthy note. So that's what I've done here. I've mixed the smokiness with the earthiness, which is what tickles your nose, to give you also that sensation of dust getting through your nostrils, like it would have happened to them. So that's what you were thinking, kind of peppery, because it tickles your nose. And that's me trying to create a sensation of dust coming through your nostrils.
That's amazing.
So that's what you've got here.
It's amazing that you can do that with like
smell.
a few kind of chemicals, and yeah, that's incredible.
Yeah. So that's the first one I've got for you.
Fantastic.
I have got the second one here. It's not that one. It's this one here. So this is the smell of Mars. Now, we obviously haven't sent any humans to Mars yet, but we do know a lot about Mars because we've been studying it for decades. So I'm going to let you smell this, see what you think.
This is very different. There's a kind of, I don't know, acidic sweetness type of thing. Yeah, it's almost like, it's almost pleasant, but then a little bit unpleasant as well. It's like, I'm not quite sure if I like the smell or not.
Okay. Probably I don't like it. And you are right. What you have here is a mixture of what we call perfume notes that are metallic and kind of like rusty metal, very cool. And there's also the sweetness you're talking about. It's a kind of metallic sweetness. That's what I was trying to create.
It's like blood. That's what it is, isn't it?
Yeah, exactly.
Yeah.
So if you think about Mars being orange, that's because it's covered literally in rust. And so what I was trying to create with this is that smell of rust that we might find on the surface of Mars. But there is something else about Mars. Obviously, the smell of Mars will have changed through its history. And there was a period of time when Mars had a lot of active volcanoes, and the smell would have been very different back then. And that's the kind of smell that you might find in places like Venus as well, or places like Io, which is a volcanic moon that orbits Jupiter. So I do have a surprise smell for you related to Mars, but also to all these other places that have volcanoes in them. So I'm gonna give you that one now. Okay, I'm not going to tell you anything about it. Are you ready for
I'm
this?
ready.
Okay, I've got it here. It's a secret thing that I've got here for you.
Oh gosh, okay.
Okay.
Why is it in a plastic bag?
Ah, well. So, with this is very gently approach it with your nose, very, very gently. Don't get too close to it. And then it will probably hit you.
Yeah, that's quite an unpleasant one.
Yes.
A bit tarry, maybe?
It's a bit tarry, but it's also very stinky.
Yeah.
If you've ever smelled a stink bomb, you have something similar in here.
Okay, so hence the Ziploc kind of
it's got a little like warning sign there that my colleague put on there. And the reason we have this one is because if you think about volcanic gases, if you've ever been near a volcano, you may have experienced the smell of rotten eggs. So that's actually what you've got.
That's sulfur, isn't it? We talked to Richie this morning, who was explaining what volcanoes smell like as well. So
that's what that is. So
that's intense.
Yeah, that's very intense. And that's one of them that I don't normally have out because we don't want the whole place smelling of rotten egg. And the last one I've got here that I'm going to give you is one of my favorite ones. This is a smell that is related to not just the Milky Way, but a specific molecular cloud near the center of the Milky Way called Sagittarius B2.
I can already smell it. So I feel like this has a little bit of that gunpowdery, maybe kind of vibe, but also the sweetness. There's definitely like a sweet, I'm not going to say rose, but it's, I don't know, there's some kind of flowery or fruity sweetness to it.
Fruity. Do you smell the sort of alcohol as well? Or like
that's
almost
true.
like nail
a nice
polish.
cocktail, yeah.
Yeah. So this is what I like to call my space party smell. And the reason, so when you go out into deep space, there are, so many molecules out there. Some of them don't have smell, like helium or hydrogen, but some of them do have smells. Some have horrendous smells, like hydrogen sulfide, rotten eggs, and others are a bit nicer. And when we looked into this particular part of the Milky Way, we detected many things, including a molecule called ethyl formate. And ethyl formate captured the imagination of so many people because it's a molecule that you find inside fruit on Earth.
Yeah.
And you find it inside raspberries. So next time you eat a raspberry, you can think you're eating a molecule that's in the center of the Milky Way. But in reality, ethyl formate does not smell like raspberries. It smells a little bit like nail polish, and there's an alcoholic rum type of smell. So what I have done there is create a blend of raspberry notes with acetone and sort of nail polish type of notes and rum alongside the ethyl formate molecule to give you that space cocktail that you have at your space party at the center of the Milky Way.
Oh, it sounds like a fun party. Definitely one that I would love to join. Thank you so much, Marina. I mean, not only is the way you describe all of this so poetic and beautiful, but I really enjoyed smelling all this stuff, and I feel like I've been on this stellar journey, so thank you very much.
You're welcome.
She's taken those samples to conferences around the world and even to NASA to use it for outreach purposes, to sort of inspire kids to follow the science route.
Did you think of replicating the smell inside the Apollo capsule after like 10 days of 3
Or 10 years on the International Space Station. Yeah. All right, now we'll close by looking at the Swift Observatory and the decade of its discovery. You'll see a picture over on the right-hand side there, and also showing the size relative to technicians. So this thing weighs a few tons. This is the one that has to be pushed up to a higher orbit by this mission that's going to occur soon. The video comes from NASA Goddard, and the audio is Action by a composer called Infraction. The spacecraft not only detects the initial burst of energy when it detects something and then swings around onto it, but it also measures ultraviolet and the visible and also in the X-ray region all at the same time. So in other words, it's got multiple instruments on it, so it tries to track the afterglow of any burst over time in those multiple wavelengths. And so far, on average, over its lifespan, it's found about 100 of these bursts per year. So it's very, very popular. And of course, other astronomers around the world then swing their bigger instruments around, Hubble swings around, that sort of thing. So it was launched in 2004 and still operational, but it won't survive more than a few months before it comes crashing down to Earth if they're unsuccessful with this robotic rescue mission. And this goes for about 2 or 3 minutes. And to actually build it again and send up the equivalent, it would be about $250 million. So as you see, there's a bit of an incentive to throw about 30 million at this rescue mission. So pretty cheap when you think about it, $30 million to put something up to try and save it. So it's widely recognised as being the most productive orbiting telescope that's ever been built, and that takes in Hubble and all the others to date. So this is like the cream of the cream. All right. With
on that, you said it's able to detect gamma ray bursts from any direction.
Yeah.
And how does it do that?
I don't know. I'd have to look that up. I don't know how directional the gamma ray bursts are. It might be very wide field that you're getting, and all it takes is anywhere in the field of view, and it'll immediately turn around onto it. So it's quite interesting because there's no onboard fuel, so it can only reorient itself using gyroscopes. And it had 4 gyroscopes, and originally 2 of them failed. But if you remember a time back, the Hubble Space Telescope had troubles with losing gyroscopes, and they actually got around it using software. In fact, that craft, it is running on 2 gyroscopes only, so they thought at one stage that they were going to lose it in the same way with Hubble, but as you see, Hubble kept going after they figured out a way to it's not perfect, but it was better than losing it. All right, well with that...
Am I right in saying that was designed with a 2-year lifespan, it lasted 20 and they're going to extend it by 10?
Correct, yeah. Absolutely, and if they extend it by 10, if they thought the other one was 2, it might be up there 50 years from now, particularly if the sun is not very active cycle, so it's not going to come down again due to the friction of running into a few molecules of oxygen up there, or atoms of oxygen. All right, well with that we'll close early and see you all with the July meeting. Okay.